All right, so I'm going to talk about a very similar open problem to Yoav's. Okay, so what is the setup? I'm looking at online linear optimization problem. So there is a given convex set in Rn, and we play according to the following protocol. So we choose a point in this convex set, and then we receive a loss vector from Rn, and we suffer the loss, which is the dot product between our choice and the loss vector. Okay? And our goal is to keep the regret small. So what is regret? Regret is the algorithm's loss compared to the loss of a strategy that chooses the same fixed point in the convex set. And I will focus on two particular convex sets that are of practical interest. So one is when the convex set is the whole space Rn, and the other one is the simplex. So that's the problem that Yoav was referring to, learning with expert advice or decision theoretic online learning problem. Now, so people worked on two types of adaptivity for these problems. So on a high level, so the first adaptivity is what I call adaptivity with respect to the competitor U. Some people call it parameter-free algorithms. For experts, this is called as quantile bounds that Yoav talked about. And the other type of adaptivity is adaptivity to the scale of the loss vectors. And each of these adaptivities separately have been achieved for both of the problems, both for the unconstrained set and experts. And so the question really is, the open problem really is, can you achieve algorithms that are adaptive in both senses at the same time? In other words, can you have doubly adaptive algorithms? Okay, so what is known? So basically, there's this very general theorem that holds for any convex set. So if you give me a strongly convex regularizer defined on this convex set, so it's one strongly convex function with respect to some norm, then I can create an algorithm that is basically just follow the regularized leader, and if I use learning rate eta, then what you can show is that its regret is bounded by this expression that depends on the regularizer and the sequence of loss vectors. Now, if you choose learning rate in this particular way, you can show that the regret is bounded by square root of the value of the regularizer times the sequence of times this expression that depends on the loss vectors. The problem is that you cannot actually do this tuning because it depends on quantities that you don't know. And in particular, you don't know the competitor U that you're competing with, and you don't know this quantity that depends on the loss vectors. So this is basically a cheat. Nevertheless, basically, we would like to achieve this ideal bound that holds for all U's without the knowledge of anything about the loss vectors simultaneously. Okay, so people worked on it fairly hard. So what is known for the expert setting? So if you use the regularizer, which is the KL divergence between a fixed prior, think of uniform distribution over the experts, then you can show that there exists algorithm that adapts to the loss sequence called ADA hedge, which achieves basically the same thing as normal hedge does, but it doesn't need to know it doesn't need to know anything about this term. Then there was a lot of, so that's one form of adaptivity. The other form of adaptivity that you can get are these quantile bounds. So you can achieve basically, so if you assume that the losses are bounded by 1, you can achieve the following bound. So there have been a lot of work by many people in this room. And then what we found out recently that by combining ideas from two papers, you can achieve essentially what we are looking for, except that the algorithm uses more memory and takes more time than all the other algorithms. So we would like to have an algorithm that is linear in the number of experts. Okay, so that's the expert setting. Now the unconstrained optimization. So if you consider the regularizer quadratic regularizer, then what you can show is that there exists a version of tuning the learning rate such that you essentially get the right dependency on the sequence of loss vectors, but the dependency on the norm of the competitor is wrong. This power 2 is wrong. What you would like to have here is 1. And now, on the other hand, if you know that all the losses are bounded by 1, you can bring down this power to 1 at the expense of an extra log factor. And there have been several papers that showed this. Okay, so the open problems are as follows. Come up with a linear time algorithm for experts, so linear time per round, that achieves the same bound as the algorithm that I mentioned. And then the second open problem, for which we offer $100, is to come up with an algorithm for the unconstrained set, where you have basically linear dependency on the norm of the competitor, possibly up to some polylogarithmic factors, and the right dependency on the sequence of loss vectors. So that's it. Thank you. So in the interest of time, I think we'll take questions.